It is the first mission devoted to mapping the moon's gravity field. NASA's Grail B spacecraft has joined its twin, Grail A, with both circling the moon.
The moon has always been our silent companion, a glowing beacon in the night sky, familiar yet untouchable. More than 50 years after humans first set foot on its surface, we still believe we know its secrets. But recent discoveries have shaken that confidence. Geophysical research letters indicates the moon has pit craters which could be turned into caves. The moon may not just be a stepping stone to the stars. It could be the most dangerous world we've ever faced. And this has even been confirmed by the one and only Keith Cowing. What is the most dangerous place on the Earth's only satellite? Let's find out. Moonlight and mystery. For as long as humans have tilted their heads toward the sky, the moon has been our most constant companion. Night after night, its pale light washes across the Earth, casting shadows, stirring myths, and guiding explorers of old. To ancient civilizations, it was a deity, a guardian, a timekeeper that regulated tides and marked the passing of months. Even now, in an age of satellites and space telescopes, there's something hypnotic about that silver disk suspended in darkness. We can trace its craters with the naked eye, map its maria with binoculars, and watch its phases dictate the rhythm of the night. Yet, despite this intimacy, the moon remains a place of mystery. It has been more than half a century since Neil Armstrong placed humanity's first footprint on its surface in 1969, followed by Buzz Aldrin under the watchful gaze of millions glued to their television sets. In the years that followed, 12 astronauts would walk the lunar surface, collecting rocks, conducting experiments, and proving that human beings could not only reach another world, but survive there, if only for a short while. Those missions, part of the Apollo program, provided groundbreaking insights into lunar geology and Earth's cosmic neighborhood. But they also highlighted the challenges: extreme temperature swings, radiation exposure, and an environment utterly hostile to human life. After the final Apollo mission in 1972, we stepped away, retreating back to Earth with a sense that the moon story had only just begun. For decades, the moon has been called a dead world, a barren rock without atmosphere, without weather, without life. But that description, while technically accurate in many respects, oversimplifies its reality. Scientists have come to realize that the moon is a place shaped by billions of years of cosmic violence, by asteroid strikes and solar radiation, by forces that continue to shape its surface even today. Its dust is more abrasive than sandpaper, its silence deeper than any place on Earth, and its isolation absolute. To stand on its surface, as astronauts once did, is to exist in a realm where every breath, every heartbeat, depends entirely on technology brought from home. Insiders within the space community often describe the moon as both our most inviting and most deceptive target. Its proximity, it's only about 238,000 miles away, just 3 days travel by spacecraft, makes it seem like the easiest stepping stone into the cosmos. Yet those who have studied it closely insist that the closer we look, the more dangerous it becomes. The moon's lack of atmosphere exposes everything on its surface to the full force of solar radiation and micrometeorite impacts. Its weak gravity, just 1/6 that of Earth, creates challenges for mobility and stability. And then there's the regolith, the fine powdery dust that clings to everything, infiltrates machinery, and threatens the health of astronauts who inhale even the smallest particles. These dangers are obvious, visible, unexpected. But beneath the moon's serene glow lies something else. A danger that does not appear in photographs or through telescopes. A danger that scientists once thought impossible in a place so seemingly inert. Reports from mission planners and researchers hint at phenomena that defy common sense. Conditions in certain regions that could turn the moon from a promising outpost into a perilous trap. The unsettling truth is that the greatest hazards may not be the ones we can see, but those that are hidden in the shadows, waiting to be discovered. For all its beauty, the moon is a world of extremes. A place where human ambition collides with nature's indifference. And as we prepare to return, not for days, but for months and years, the stakes are higher than ever. The question is no longer whether we can reach it. The question is whether we truly understand it. Because in the heart of its silence lies a secret, a danger that should not exist at all. And yet it does. Water, where it shouldn't be. For generations, the moon was assumed to be bone dry. Astronauts from the Apollo missions brought back more than 838 samples of lunar rock and soil, and initial analyses found no signs of water. The prevailing belief was that without an atmosphere to shield it, any trace of moisture would have long ago boiled away into space. But in 1976, a Soviet spacecraft quietly planted the first seed of doubt. That spacecraft was Lunar 24, an automated probe that drilled nearly 2 m beneath the surface of Markium and returned a soil sample to Earth. Soviet scientists announced that their analysis showed water in the lunar regolith, small but measurable amounts. Western experts at the time dismissed the finding as contamination, suggesting the samples must have been tainted by moisture once they were back on Earth. For decades, the claim was largely forgotten, filed away as an anomaly. Yet, insiders in the lunar science community often whispered that perhaps Lunar 24's result deserved more attention than it received. The next hints of water came not from landers, but from orbit. In 1994, the US launched the Clementine mission, a joint project between the Strategic Defense Initiative Organization and NASA. Clementine's radar measurements suggested there might be ice hidden at the moon's poles, buried in craters that never see sunlight. The evidence was circumstantial but tantalizing. Only a few years later, Lunar Prospector, launched in 1998, added weight to the theory. Its neutron spectrometer detected hydrogen signatures near the poles, which many scientists interpreted as a strong indication of frozen water mixed with soil in permanently shadowed regions. Still, ambiguity lingered. Hydrogen could point to water, but it could also point to other compounds. What researchers needed was confirmation, and it would come from an unexpected corner of the world. In 2008, India's Chandrayaan-1 spacecraft began orbiting the moon. On board was the Moon Impact Probe, which detached and slammed into the lunar surface near the South Pole. Chandrayaan-1's spectacular egg scheduled to orbit for 2 years. The space shuttle is expected to collect vital information. Instruments aboard recorded data during descent. And when scientists later examined the results, they reported something extraordinary. Evidence of water vapor released upon impact. Even more convincing was Chandrayaan-1's Moon Minology Mapper, a NASA-built instrument designed to scan the surface. It detected absorption features consistent with hydroxyl molecules, chemical signatures that could only be explained by the presence of water or water-related compounds bound within lunar minerals. By now, the tide was turning. The question was no longer whether water existed on the moon, but how much and where. NASA sought to answer that directly with one of the most daring experiments of the modern space age. In 2009, the ICROSS mission, short for Lunar Crater Observation and Sensing Satellite, was launched with a bold plan. The spacecraft deliberately crashed a spent rocket stage into the Koos crater near the lunar South Pole. A trailing probe then flew through the debris plume, analyzing its contents before meeting its own violent end. The results shocked even seasoned researchers. Instruments detected clear signs of water ice mixed with dust in concentrations far greater than expected. Some estimates suggested there could be hundreds of millions of metric tons of water locked in the polar regions. The discovery made headlines worldwide. The moon once thought to be a desert held resources that could support future explorers. But here is where the intrigue deepens. While LCS confirmed water ice in one crater, other surveys have produced conflicting results. Some craters expected to harbor ice appear barren, while trace amounts of water seem to appear in regions where scientists believed it should be impossible. The Moon Minology Mapper even suggested that water, or at least hydroxyl, migrates across the lunar surface, forming and disappearing with the daily cycle of sunlight. This dynamic behavior was utterly unexpected. Reports from NASA scientists describe it as water where it shouldn't be. Instead of neat reservoirs of ice locked safely in the shadows, water appears patchy, mobile, and in some places inexplicably abundant. The picture is uneven and confusing. For every crater that seems to promise a frozen treasure trove, another defies the models. This puzzle has kept researchers cautious. Yes, the moon has water, but not in the straightforward way we once imagined. It is hidden, scattered, and sometimes fleeting. And just as quickly as evidence builds, it also raises new uncertainties. The moon has never been simple. And as explorers look to it not just as a destination, but as a stepping stone to deeper space, they are forced to wrestle with an unsettling reality. What we thought would be our most reliable resource may be more elusive than we ever dreamed. The promise in the puzzle. Now, let's consider the facts. If water truly exists on the moon in usable quantities, it could change the course of space exploration forever. For colonization efforts, water is a necessity. Future astronauts will need it to drink, to irrigate crops, and to support long-duration stays on the lunar surface. But the value of water extends far beyond life support. With the right technology, water can be split into hydrogen and oxygen. Oxygen provides breathable air, while both hydrogen and oxygen can be liquefied to create rocket fuel. That means a lunar outpost with access to water could refuel spacecraft, enabling voyages deeper into the solar system at a fraction of today's costs. Instead of hauling every pound of fuel from Earth, missions could use the moon as a fueling station, transforming it into the true gateway to Mars and beyond. Reports from space agencies have put numbers to this promise. Every pound launched from Earth costs thousands of dollars in rocket fuel and resources. If water could be sourced directly on the moon, it would slash those costs dramatically, allowing missions to carry more equipment, science payloads, and life support systems instead of bulky propellant tanks. In many ways, lunar water is the key to making a sustainable human presence in space possible. Yet, the deeper scientists look, the more puzzling the situation becomes. One of the most surprising findings came from the Lunar Reconnaissance Orbiter or LRO, which began circling the moon in 2009. Using spectrometers and thermal sensors, LRO detected faint but measurable amounts of water across regions exposed to sunlight. The readings implied that water, or at least hydroxyl molecules, could be forming and disappearing on a daily basis. It suggested the existence of a fragile lunar water cycle where molecules migrate across the surface as temperatures rise and fall. This was never expected. For decades, the conventional wisdom had been that water could only survive in the moon's coldest and darkest craters. The idea that it might exist in sunlit areas challenged everything scientists thought they knew. The polar regions, though, are still the most compelling targets. Certain craters at the lunar poles never receive a ray of sunlight. These permanently shadowed regions or PSRS are some of the coldest places in the entire solar system. Temperatures there can plunge below -400 degrees Fahrenheit, creating conditions where ice could remain stable for billions of years. To scientists, these craters function like natural deep freezers, locking away whatever volatile materials like water might have landed there. For explorers, they are both a promise and a peril. Rich potential resources trapped in environments more extreme than any on Earth. But how did the moon get its water in the first place? Several theories compete. One explanation points to cometary impacts. Comets, often described as dirty snowballs, are loaded with water ice. A comet smashing into the lunar surface could scatter fragments of ice, some of which might survive in the cold traps at the poles. Another possibility involves the solar wind. Streams of charged particles from the sun constantly bombard the moon's surface. When these particles strike lunar soil, they can interact with oxygen in the minerals, forming hydroxyl molecules, and in some cases, water. A third theory involves micrometeoroids, tiny bits of rock and dust that slam into the moon at high speeds. These impacts may briefly generate enough heat and pressure to create glassy beads in the regolith. Beads that sometimes contain traces of water locked inside. Each theory has evidence to support it, but none fully explains the distribution of water scientists have observed. Why is it patchy? Why does it appear in unexpected places? And how much of it can realistically be accessed? These are questions that researchers continue to debate. Insiders admit that despite decades of study, the moon keeps surprising them with every new data set. For humanity, though, the bottom line is clear. The presence of water, no matter how scattered, no matter how puzzling, offers a beacon of hope for colonization. It means the moon is not just a barren rock, but a world with the potential to sustain life and extend our reach into the stars. The challenge is learning how to harness that promise while solving the mysteries that refuse to give us simple answers. The world of terror. When most people imagine danger on the moon, their minds go to obvious extremes. Volcanic calderas scar the surface, reminders of an ancient era of molten activity. Radiation from the unfiltered sun bombards everything in its path. Even the vacuum itself is hostile to life. But according to researchers, these are not the most perilous spots humanity must contend with. The true danger lies in places that appear calm, silent, and even promising. Places where explorers dream of harvesting ice to fuel missions to Mars. Places that by every logical assumption should be safe. And yet they are not. And now one NASA insider revealed the most dangerous places on the moon, and it's bad news. The expert talked about permanently shadowed polar craters known as PSRS. These craters sitting near the lunar north and south poles have rims that block sunlight year-round. Temperatures inside them can plummet to levels colder than Pluto, preserving any ice that finds its way there for billions of years. To scientists, they seemed like natural treasure vaults, storing the water resources that could sustain colonies and propel spacecraft deeper into the solar system. But new research has revealed something unexpected. And believe it or not, this changes everything. It turns out these craters may become electrified, charged to hundreds or even thousands of volts. The culprit is the solar wind, a constant stream of particles from the sun. Because electrons are far lighter than ions, they move faster and reach the lunar surface first. When these electrons pour into the shadows of the craters, they accumulate along the walls and floors, leaving behind a massive imbalance of charge. The result is a hidden electrical field, an invisible hazard lurking inside the very places astronauts are most likely to explore. Reports from Universe Today, Space.com, and NASA's Scientific Visualization Studio have highlighted the danger. These craters could act like natural batteries with uneven electrical potentials strong enough to disrupt technology and endanger humans. Instruments suggest that static discharges could jump from one surface to another, frying delicate electronics or short-circuiting rovers. For astronauts, a sudden discharge could be catastrophic. A suit designed to protect against micrometeorites and radiation might not withstand the jolt of a high-voltage arc in an environment where grounding is almost impossible. The dust only makes matters worse. Lunar regolith is infamous for being abrasive, sharp, and clinging to everything. When electrified, it becomes even more hazardous. Electrostatic forces could cause dust to float or stick to surfaces unpredictably, coating visors, solar panels, and life support systems. Machines could grind to a halt under layers of gritty charged particles. And for humans, any breach that lets dust infiltrate living quarters would create serious health risks. Some scientists have warned that inhaling lunar dust could be as harmful as breathing in fine glass shards, cutting into lungs, and causing irreversible damage. Keith Kine, a longtime NASA commentator and editor of NASA Watch, has underscored how overlooked these dangers have been. In his words, lunar exploration has often been framed as a matter of engineering solutions, stronger rockets, better habitats, smarter robots. But when the environment itself generates invisible electrical hazards in regions once thought ideal, the challenge becomes far more complicated. What makes this revelation so unsettling is the contradiction at its core. The polar craters are where we expect to find the moon's greatest riches. They are supposed to be the key to survival, a source of water, fuel, and the promise of permanence. Instead, they are electrically unstable environments capable of sabotaging the very missions that seek to unlock their value. It is a danger where there should be security. It is a peril hidden inside hope. For astronauts, every step into those shadowed valleys could carry a risk far greater than slipping on the dust or braving the cold. Without grounding, even a single movement could build up enough charge to trigger a spark, forcing explorers to stop and bleed away electricity before moving again. The vision of easy water extraction now seems fraught with obstacles. So, yes, the serene, silent companion of Earth holds secrets we never imagined. The challenge of safe extraction. The discovery of vast water reserves hidden within the moon's polar regions once sparked bold visions of mining operations, fueling colonies, and transforming humanity into a truly space-faring civilization. But as often happens in exploration, excitement collides with reality. The dream of tapping into the ice deposits tucked away in permanently shadowed regions is now complicated by an invisible, unpredictable threat. Extracting water from these craters may be far more treacherous than anyone initially expected. The consequences are immediate and sobering. Engineers and mission planners can no longer assume that these polar sites are simply frozen vaults waiting to be opened. Instead, they must grapple with a landscape shaped not only by extreme cold and darkness, but also by electrical forces strong enough to jeopardize survival. This means every piece of equipment from drilling rigs to solar-powered rovers must be tested not just for endurance in sub-zero conditions but also for resilience in volatile electrostatic environments. The implications are even more personal for the astronauts. Spacesuits designed for protection against micrometeorites and thermal extremes may not be enough. If electrical charges accumulate on the surface or within the suit itself, the wearer could unknowingly carry thousands of volts of static potential. One careless movement or one exposed connector could trigger a spark strong enough to disable systems or cause injury. That possibility alone reshapes the calculus of lunar exploration. Safety now depends not only on shielding against cosmic rays and maintaining thermal balance, but also on preventing astronauts from becoming part of the circuit. To address this, innovations are underway. Materials scientists are experimenting with fabrics and polymers capable of dissipating charge, weaving grounding threads directly into the layers of next-generation spacesuits. These designs may allow explorers to safely bleed off charge before it builds to dangerous levels. Similarly, engineers are developing tools with conductive coatings ensuring that every drill, probe, or sampling arm remains electrically neutral even in volatile environments. Of course, at the same time, the problem of dust cannot be ignored. Lunar regolith is notoriously sharp-edged, clingy, and difficult to remove. In charged environments, its behavior becomes even more troublesome. NASA researchers have been testing electronic dust shields, thin films that use oscillating electrical fields to repel particles before they can cling to surfaces. Early trials suggest this technology could be applied to visors, camera lenses, and even solar panels, maintaining functionality where otherwise layers of dust would build up and compromise performance. Other proposals lean on cryogenic methods such as dust capture systems using sprays of liquid nitrogen to freeze and remove grains before they become destructive. Each of these ideas represents a step toward overcoming what may be one of the most stubborn obstacles in lunar history. But the stakes go beyond engineering challenges. Imagine a rover descending into a crater, its instruments calibrated for drilling into ice-rich regolith. Before it can complete its mission, a sudden electrostatic discharge races through its circuitry, frying its systems in an instant. Billions of dollars in hardware could be lost, along with months or years of preparation. The Grail mission and gravitational mapping. In September 2011, NASA launched the Gravity Recovery and Interior Laboratory, better known as the Grail mission, aboard a Delta II rocket from Cape Canaveral Air Force Station in Florida. The spacecraft were named Ebb and Flo by schoolchildren through a nationwide contest, and they entered lunar orbit around New Year's Day 2012. Unlike other lunar missions that focused on surface exploration or sampling, Grail was designed to probe the moon's hidden interior by mapping its gravitational field with unprecedented precision. The two nearly identical spacecraft flew in tandem, maintaining a controlled formation while measuring minute changes in the distance between them caused by subtle variations in the moon's gravity. These changes, on the scale of microns, provided scientists with a way to see beneath the lunar crust and examine density differences in the subsurface that no camera or lander could reveal. The mission lasted until December 2012, when both spacecraft were deliberately crashed into a mountain near the lunar North Pole after depleting their fuel reserves. Despite operating for less than a year, Grail revealed paradigm-shifting insights. The spacecraft collected some of the most detailed gravitational data ever obtained for any celestial body. Its measurements were about 100 times more precise than those made by previous missions such as Lunar Prospector in the late 1990s. The dataset offered a complete gravity map of the moon, resolving features as small as 20 kilometers across, which represented a dramatic improvement over earlier maps that could only detect features larger than 100 kilometers. One of the major scientific results from Grail was the confirmation that the moon's crust is thinner than previously thought. Earlier models had suggested crustal thicknesses of up to 60 kilometers, but Grail's data showed that in many regions the crust is closer to 34 to 43 kilometers thick. This finding had profound implications for theories of lunar origin, particularly the widely accepted giant impact hypothesis, which proposes that the moon formed from debris generated when a Mars-sized body struck the early Earth about 4.5 billion years ago. A thinner crust implied that the moon's early history of magma ocean crystallization and differentiation was more complex than we thought. Grail's gravity maps also revealed a surprising level of structural asymmetry between the lunar nearside and farside. The side facing Earth, known for its dark basaltic plains called Maria, showed evidence of large gravitational anomalies linked to ancient volcanic activity and concentrations of heat-producing radioactive elements in the mantle. By contrast, the farside, which lacks extensive Maria and remains heavily cratered, displayed a more uniform but rugged gravitational landscape. This asymmetry helped explain why volcanic eruptions were far more common on the nearside while the farside remained geologically quiet. The research team analyzing these findings included scientists from multiple institutions, with Ryan Park of NASA's Jet Propulsion Laboratory in California playing a central role in refining the interpretation of Grail's gravity data. By applying sophisticated models of tidal deformation and mantle dynamics, Park and his colleagues demonstrated that the nearside mantle is more deformable under Earth's gravitational pull than the farside mantle. This confirmed that the two hemispheres of the moon are not only geologically distinct on the surface but also fundamentally different deep inside. The likely cause was an uneven distribution of radioactive isotopes such as thorium and potassium, which continue to produce residual heat billions of years after the moon's formation. Another important contribution of Grail was its ability to trace the origins of lunar basins and impact structures. The mission revealed that many large basins, including the Imbrium and Orientale, have ringed structures extending deeper into the crust than previously realized. These gravity signatures suggested that the moon's crust and mantle responded elastically to colossal impacts, and that these events shaped the moon's geological evolution more profoundly than surface imaging alone could show. The findings also provided a valuable comparative framework for studying impact processes on other planets and moons in the solar system. The precision of the gravitational field data from Grail has continued to serve practical purposes for modern lunar exploration. High-resolution maps improve navigation and orbit determination for spacecraft, ensuring that future missions such as NASA's Artemis program and international lunar landers can achieve greater landing accuracy. They also assist in identifying regions with resource potential, such as areas where concentrations of titanium or thorium may be more abundant. But that's not all. In fact, we're only getting started. The moon is not what we thought at all. Discovery of lunar flexing. For long, it was assumed that the moon was shaped primarily by ancient impacts and volcanism billions of years ago. Yet recent analyses of lunar data, especially from NASA's Grail mission, have revealed that the moon is still undergoing a subtle but measurable process known as tidal deformation. This phenomenon is caused by Earth's gravity, which exerts a constant pull on the moon. Although the deformation is extremely small, on the order of tens of centimeters, it provides valuable clues about the interior structure of our nearest celestial neighbor. The concept of tidal deformation is familiar on Earth, where the gravitational pull of the moon generates ocean tides that rise and fall twice daily.